So suppose you're given the following vector field f equal to 6 x squared y, and then 2x cubed. Okay, let C be the curve given by the following. T minus 1 to the third power plus square root of 2t, comma, t squared plus 5t plus 1. And let's say t goes from 0 to 2. And the question is, compute integral of f dot dr over this C. And if this was the only thing that was given, it's a little harsh because, as you can see, trying to differentiate this and plugging them in here and then doing the integral would not be so fun activity to do, right? Do you think you can just directly compute this? It's going to be horrible. You kind of see how horrible it is, right? You have to differentiate this. That's your dr over dt. And then you have to evaluate this function over these points. So you have to plug that in here. You have to square it times this thing. You have to expand. It's not pretty, okay? But here is the interesting hint. F is conservative. Or check that F is conservative, okay? So that's the hint. Okay, so let's try it. Solution. So you're looking at this question and look at the hint and say, okay, so I have to check that f is conservative. Really? Let's say if I take x derivative, y derivative, and put 6x squared y, 2x cubed. Let's see. This hitting this, what's that? 6x squared, right? Minus this hitting this. If you differentiate this by y, right, what's that? That's 6x squared again, which is 0. So yes, it is conservative. Okay. All right. So what? What's the good thing about being conservative?
The events are like constant.
Huh?
There's acting like the x and y just by themselves.
Well, okay, so being conservative means that there's a function f whose gradient is equal to this. That's what we know. But there was another important fact about computing line integrals for conservative vector fields. Do you remember? Since f is conservative, we know that the integral of f dot dr of C is equal to f xy evaluated at point B and A. Okay? What is this small f? It's the function whose gradient is this, right? So if I can find out that function, all you have to do is take that function and evaluate it at the endpoints. I'm done. That's the beauty of this question. Okay? If we can't use this, then the only other option for us is to do this horrible, horrible computation, which is going to take about an hour for me. Okay? I don't know how much it's going to take for you if it takes an hour for me to do it that way. So it's all right. So definitely this is the right way to approach it. Okay. All right. So let's try that. What kind of function has the following property? F differentiated by x gives you 6x squared y. What does that mean? That means f should equal to, if I integrate by x, what do I get? Take this and integrate by x, what do I get? What? Integrate.
Oh.
This is already differentiated by x. I want to do it. Yes.
2x cubed.
2x cubed y, right? Okay. Plus some function of y, right? Now, if f differentiated by y is equal to this part, 2x cubed, what should be your function f? If I integrate this by y, what would I get?
2x cubed 1.
Right? And then you could have a function of x. But wait, I can just set them equal to 0 and they're going to match, right?
Yeah.
That can happen, right? Sometimes one of them could be 0, sometimes both could be 0. Sometimes they might, none of them could be 0. But right now you can see that since I don't have any function of y by itself, this must be 0, right? And this description says, oh, I don't know this function of x, but if I look over here, oh, it's a function of x by itself, right? So from here, I can conclude that if I take fx comma y as 2x cubed y plus some constant c, right? If I just let both of these to be just a constant c, right? Then this perfectly works, right? You take this function and do a partial with respect to x, you get the x component of the vector field. If I take this and do a partial with respect to y, I get the y component of the vector field. So that's a perfect fit, right? Okay. And then, and by the way, since we are really doing a definite integral here, just like in the case as in Calc 2, where when we do definite integral, you don't really have to think about this because that cancels away, right? So this is not needed for this type of question because you're using it for definite integral. So I mean, you can have it, leave it there. It's gonna cancel anyways. But for this one, you don't need the c. Okay. So that's our fxy. Now we have to figure out what the beginning point and what the ending point is. Okay. So let's try that. When t is 0, where is the point beginning? Where does the curve begin?
0. Alright.
0 minus 1 cubed. So negative 1 cubed is negative 1. If I plug in 0, is 0. So I know that r evaluated as 0 is 0. And then if I plug in 0, what do I get? Oh, sorry, so it's just negative 1, right? Negative 1. And if I plug in 0, what do I get? I get 1, right? If I plug in 0, negative 1 cubed gives you negative 1. This gives you 0. 0 plus negative 1 is negative 1. If I plug in 0 here, I get 1. Okay, so that's my beginning point, point A. Okay? And then where does it end?
3.
At 2, if I put 2 minus 1 is 1, 1 cubed, so it's 1. 1 cubed is 1. If I plug in 2 times 2 is 4. Square root of 4 is 2. 2 plus 1 is 3. If I put 2 here, let's see, that's rather big. 2 squared is 4, 2, 10, 11, 15. Is there? Okay. That's 15. That's your B. And we're almost done. Now we can just simply say I need to do 2x cubed y. Evaluate at these points. 3, 15 is your ending point. Your beginning point is negative 1, 1. So it's I mean, I don't even know what's the shape of that path, but it's some strange curve which begins at this point and ends at that point. And because the given vector field is conservative, which we checked, right? In that case, we can use this wonderful theorem. Okay? And therefore, let's see, if I evaluate here, 3 cubed is 27, 405 times 2, 810. If you plug this here, you're going to get 810. If you plug this in here, you get negative 2. So 812 should be your answer. Okay. And that's what you call amazing. It's the amazing property of conservative vector fields. See, just to realize how awful this question could be, say I put plus x, this right here, plus x. Right? If it's plus x, then the derivative will have plus 1 there because I have to differentiate this by by x. So if it was 2x cubed plus x, that plus x will produce plus 1 here. So this will give you negative 1. That means the vector field is not conservative. If it's not conservative, can we use this? No. Then you have to go through all that. We have to just do all this calculation, and it becomes a whole mess. But just because we were able to figure out that it's 0, now we have a very easy answer. Easy compared to the other nightmarish scenario.